Okay, that's the boilerplate at the front. I'm Howard Brooks. Going to talk about pre-burst chaos. We've had some fun on the mailing list talking about that through the spring, and so I just thought we'd do a little bit of fun and show you a few things and talk about it. And then, since in my day job I actually do work at that place, I did a sort of geeky simulation to show that it can happen, even though we know it happens. So we're going to start off with a video here. Now, how do I get that one? Zach, is that what this? Yeah, that's what I need. And then watch the sound when it first comes. Well, I have to watch the play when we get there. Yeah, the sound can be off so I can talk over it once. Because my mouse isn't doing anything. Oh, is it? Yeah, maybe it is, except I can't see. There we go. This is fun. You want to try that? Well, no, you drive, because I'm trying to drive sideways, and I'm not very good. You just go ahead and bring it out and hit the play. Is it playing, or is it still paused? Well, it's probably buffering, isn't it? This is really exciting. This is a video taken from a workshop that was done. The launch was out of the north side of Indianapolis for a bunch of middle school and high school teachers. A fairly ordinary upward pointing camera. Okay, and this video, if it gets buffered and runs at normal speed, takes 2 minutes and 56 seconds. And all this is, like I say, November of last year. Jason Krieger, the president and CEO of Stratostar Systems, is the one who did the flight. And so it's going to eventually maybe play a little faster than that. It goes up fairly ordinary. He was climbing at about, if I remember right, 1,400 feet per minute. I keep moving, John. I can get out of the field no matter what. You know, I can make that work. It's one of those things. If this doesn't play any faster, we may skip on my own. You just watch a second here. We'll just watch one part of it. Hopefully it'll buffer up fuller and bring us through. So he skipped a few frames. Now watch somewhere in a moment, all of a sudden we'll see a horizon or a ground shot coming as we work through it. Yeah, that's right. That's right. That's something else. If this doesn't play much faster, we'll go past it and go to the stills from another flight. We're getting higher now. Here we go. Now we're going to. Now it's getting closer to running at normal speed. Maybe. There you go. So that was just a loop-to-loop, you know. So my buddy Ron is in the coasters, right? So that's just what we just did. We just did a loop-to-loop. And then he kept on climbing for a while. Nothing terribly ordinary happened. It keeps on climbing. And in a moment, we'll get to where I've lost the clock down in the corner to tell us where we are in the video, but we'll get to the point that it decides to get really chaotic if it gets out of there. Where did they hide escape? Oh, this side. Yeah. Let's just try to get down where we can see the. Okay. Yeah, I was trying to get down just to see the clock, see how far we are in our 2 minutes. That's not saying it yet. Well, let's go to full screen again. Can you hit that button for it? Yeah, that's full screen. Okay. There we go. Full screen what? Yeah. Full screen, I didn't say what. Okay. I wish we did. How buffered is it? Well, maybe we'll just exit out. I'll go ahead and show the stills of the other one. It'll be just as good. We're getting close to the exciting time, but that's not a big deal. Let's just exit. Yeah. And now I'm back to the slideshow, aren't I? Slideshow. Oh. Okay, now at the next slide, which I can do this way. There we go. Okay, now I'm going to show you some stills from a different flight. That was November. This is actually October. It's backwards. These are courtesy of Jeff Daly. I really have access to them too because I paid $100,000 to send my son to Taylor University, and he no, that's actually both sons for $100,000. So it's not a bad deal to work through it. David's worked with me on a few flights. We launched one that knocked the power out to Upland, Indiana on our way out of town, landed in the drinking reservoir for Columbus, Ohio. And he was on one of the ones that got away and went to Athens, Ohio one time, and we stopped just short of there and stayed 6 weeks in the tree. This flight, he was part of a class of astronomy, so it's another long string of payloads like Nick showed earlier. And what happened here at about 72 kilofeet, the payloads went sideways. Then they went stable, and then they went completely horizontal again at 82 feet. So we just got a few pictures that kind of go along the way. 82.4. I just noticed here that how they're strung out, and also you can see the support strings are not twisted yet. Okay, now they are. Okay, and within the next second. So while it's out behind, it's also spinning. Okay. Well, this is a signal for who? Just wait. Okay. Here's the next picture. Okay, this is during ascent. Okay. We're at 82.6. Okay. This is the camera that we're supposed to be looking down. It is. But what it's looking down at is the parachute and the hoop, the spreader, laying on top of the balloon. Okay. Okay. There's again with the hoop. No, this is not Photoshop. Okay. The hoop did not stay balanced. The camera changed its perspective slightly. Okay. And then this is an image taken by the camera when the command pod went into the balloon. Okay. Which is the same thing that happened on another flight a month later. Okay. So it's actually breaking it. Okay. You see the tears that's going through there. Okay. And there it came out the other side. I wish you go back and use the presentation, go look at that video from Near Space Network of Jason's, because what's really impressive about it is after the stuff flies through the balloon, you have a broken balloon with everything inside it, and the camera's watching, and you can see it open back up, and it came down on full shoot just perfectly fine. I mean, it should. Well, I don't think I don't think the camera went through. I think command went through, and the camera was outside. So I mean, we haven't yet. No one yet. There's the next challenge is to have you fly your camera through the balloon. Okay, but we haven't had that happen quite yet. Okay. So anyhow, those were I think 1200s. I think sometimes they fly 1500s, but it depends on how much I had on them. I think they were 12s. I say both of those were climbing at about 1600 feet per minute type climb. I also have done some stuff through time with different accelerometers. This is the NIMSIG 2125 that I used, 2 axes. Its output comes on a duty cycle proportional square wave signal. I got that from Parallax. There's another one up here that I assume we're giving away sometime today. Okay, they have the tri-axis one. Hitachi's tri-axis is actually an analog voltage on their thing, but the way Parallax has packaged it, it still comes out as they've done the A to D conversion, which I personally don't care for. I'd rather have the voltages. Here's the theory of operation on the 2125. It's a little bubble of hot air. If everything is, if it's sitting horizontally, all 4 temperature sensors read the same temperature. If it's tilted, they read different. Convert the difference in temperatures to the amount of tilt is the idea behind it. And if you want to read the documentation, which I try to avoid plagiarism at most cost. As we look at it. Here is just data from one of those sensors. I picked base 28 because that was the last time I was with you all. Okay, that was the GPSL out of Liberty. And it was a fairly boring flight. Okay. A few exciting things just after launch, and some of us remember the launch where we had the 4 and 5 going up, and I did the best with my balloon to steer it since it was unsteerable into the tail of the balloon, and got it a little bit more than I thought, right? So we tilted pretty good as we went on the ascent. There's just normal 2 standard deviations to show that everything stayed fairly normal through the flight, just the ascent, although we did hit every once in a while little pockets where it got a little bit of a swing. Okay. Here's a different one. This is base 34. Okay, and this is a fun one because I was actually flying a commercial sensor for a guy out of the Northeast, and he was wondering what happened above 40,000 feet. And the bottom line is we hit some fairly good turbulence that gave us some pretty good tilt in one direction. This is skewed, you'll notice. The average is actually not at 0. Okay, this is what happens when students don't always check the length of their strings on their payload, and when you launch it crooked, it tends to stay crooked. But still, the swings are fairly real along the way there. And the video out of this one was not indexable, but once again, on the video, we got to see with our down camera, we saw beyond the horizon. Okay, but like I say, I can never get it indexed to where I could ever copy it out. So you have to trust me on that one. This is the accelerometer I'm using now and prefer more. It's a free scale. It's a 3-axis. The key is it comes out with analog voltages. It works off of dual capacitors. I'll show you. It's available from Sparkfun. I don't know that we're giving any away. So. Okay. Yeah. Yeah, maybe in there. But I won't take it out so you think but it works pretty good. So the basic idea I would say is it's two capacitors. Okay. The middle plate is the one that's free to move. And if it accelerates, then that's going to change the value of the two capacitances. You read the voltage across the one, and you know if it's right in the middle of your range, you're at zero acceleration. If it goes towards zero, you're accelerating one direction. Towards 3.3, you're doing the other direction. Works like a champ. We did kill one. You can kill one since they're supposed to run under 3.3 volts. If you put more than 15 volts between the sides, you're fine. The girl was trying on the breadboard real hard. She plugged in the plus, and she was going to plug in the ground. And this is an old cadet. If anybody used those cadet design boards, rather than hitting the ground row, she hit the minus 12 volt bar. And I came back in the room, and she says, "I hope you don't smell anything, but I broke it." You know, and she did, so that's okay. Here's another. This one's actually then I got real physicsy on you. Okay, rather than doing angles, this is actually acceleration in meters per second per second. Okay, the really weird unit that we like to use. And this is one out of base 43. Happens to be all these guys have been flying with the Geigers this summer. Okay, and we had this flight, and you'll notice once again some interesting things happen. I'm actually going to talk about that point that shows the 6 meters per second positive acceleration at about 28 kilofeet, okay, and a few others along the way. Okay. Well, where does this stuff come from? There's a couple of different ways to do it. For time, we won't bother to go. Actually, that link at the top is hot. We could go and see the current prediction for where the clear air turbulence happens, and the likelihood. This is just whatever I grabbed probably on Saturday when Zach was starting to holler at one of the presentations in, and I said, I'll put a screenshot in of what happens there. But gives you the likelihood. I guess Kansas made the news again. The only way Kansas tends to make the news. Somebody flying over hit clear air turbulence, right? So they had to land at Denver rather than going out west. You know, those sort of pockets. Those are some things that can cause some of the problems we have. Most of that arises just from the simple fact that you have encounters with various wind speeds. Okay, this one's in meters. Okay. So 25 k-feet is approximately, or 28 k-feet is about 8 kilometers up. The students on base 44 took this one, and they noticed they had a little kink in their data there. And I thought, well, that's interesting. And they thought, is it real? I said, well, let's go look at it closer. And it was. Okay. We're climbing. For those who know how I like to climb slow, this is a fairly fast climb for me. Okay, I mean, we're going up here to, about 300 meters per minute, so 1,000 feet per minute. That's pretty fast for my Geiger counter stuff. And we reached 8,400 meters and decided for the next minute and a half we're going to go down. Okay. And then we went back up. And once again, the video from that shows horizon as we went through that process. Okay, so we swung out. The bottom box of the camera was swung out enough to get to see sideways as we went. Yeah.
We've seen that stuff in the OSS.
Yeah.
It's reasonably low altitude,
Mm-hmm.
violent downswing,
Right.
upswings, but we've never associated it with swinging out the side. That's it.
Yeah. Like I say, watch the image, and sometimes it happens. It's kind of a fun. I'm going to try to get off and explain that. Okay. Now, talk about the other type of stuff that's there always. There's the idea about atmospheric gravity waves. So we've talked some about that. I think we talked about that at Grand Island. Even remember the idea that you come over the landform. What is that? Onography? Whatever the fancy word is for. Yeah. But over the mountains, you can have convection from the thunderstorms, frontal systems, the interfaces with the jet streams, both the polar jet and the lower jet will certainly cause some things. And some of the stuff that happens up real high is probably actually energetically particle driven. Like the stuff that, the fun thing about the flight my son was on that went sideways at 82,000, they launched another balloon 10 minutes later, followed the same path, and didn't hit anything dramatic. Okay, which gets into the fact some of these gravity waves that take place have periods of just a few minutes and wavelengths of maybe just a few tens of kilometers, and also you can pass right through and miss them. Okay. So No, there's stuff I'm supposed to say about that. There's lots of pretty pictures that you can see sometimes of the clouds that show whether it happens in troposphere, mesosphere, or it's up in the thermosphere. I don't think any of us ever get to the 90 km stuff, so but we can certainly watch for the ones that happen through troposphere and the like and all of that. Okay. So I'll talk a little about the wind flight string interaction. Okay, I'll try to bring ourselves closer to the time frame again. Okay. So the bottom line is the force through the winds proportional to the air density and the cross-sectional area of the object. Okay, and so we have the competing factors going on when the balloon goes up. The air density is going down, right? And but the cross-sectional area of the balloon is increasing. Payload boxes, on the other hand, are fixed size, we hope. Right? Sometimes they fall apart. Sometimes the wings come out, and that's but basically they're fixed size. So the balloon gets larger, as I said. Here's just some stuff I kind of played with, looking at the force on an expanding balloon at various sort of semi-standard altitudes. It's what 11, 20, and 32 kilometers. But I thought I'm dealing with aviation folks again, so I better put it in feet, right? So feet for the volume of your balloon. Okay, this is a pseudo physics balloon, right? It's like the spherical chickens we use. Don't get too excited about the dimensions that happen there. Okay. Cross-sectional area that you would see that the balloon was a 10 if you viewed it as just being a simple sphere. Okay. Look what happens to the air density. We know about that, right? We're down to 1/100th of the atmosphere and all that stuff. So this is the force. For those who don't do the conversions every day, 4.5 meters per second is basically a 10-mile-an-hour wind. Okay, and that sort of thing. The force does decrease on the balloon as we go up, but that's still a fairly significant force as you work through what could happen on the balloon. Okay. And so I did the simulations using Interactive Physics 2.5. They don't put that out anymore, but that's still what I had. And I still have computers that can read 3.5-inch floppies, so I can even bring it in and still use it. So I did. Okay. So my quick simulation, just to show you some cute pictures that we kind of did in the simulation, I assumed a 1,500-gram balloon. Okay. It turns out that if you put 300 cubic feet, well, 300 cubic feet of helium is also 1,500 grams. Okay. It's very convenient. Makes the total mass of the balloon and helium 3 kilograms. Okay. I then put on it with the interaction 3 different payloads that were on 3-meter-long strings, so roughly 10-foot strings to play the game. I made the top one 4/10 of a kilogram for no good reason. Middle one 5/10, and the bottom one 2 kilograms because I fly Geiger counters, right? And so our bottom box is not even 2 kilograms right now, but it's a good 1 3/4 kilograms that we're flying. So the total weight of the flight string is 58 newtons. And so then I just ran some simulations. Using various wind forces, okay, in a ratio to the total weight. So the horizontal is the idea of the wind. The vertical is essentially the buoyancy lift that's on the balloon. And the time scale here is conveniently arbitrary, okay? Sort of reminds me of Michael with his arbitrary pressure units, you know. Amazing. Okay. So we can see that with a general breeze acting on it, we get a little swing sideways, which once again, I agree, we may not really see. And of course, depending on how everything's mounted, you might not even notice the swing unless you really apply the tilt sensors everywhere. That's what I really encourage people to do. That's 1/3 total weight. There's wind force equals total weight, and gosh, I'm sideways, right? Okay, that's kind of cool. Okay. So I'm simulating. I can simulate and go more weight, more wind, right? And, yep, you notice a couple things. First of all, somehow I even get the middle string between these to be slack momentarily, okay, which kind of relates to those pictures we showed from Jeff, okay, and then twisting can happen. I get almost like what we saw at the end of the other one, but this going one more time frame, I'm up there, okay. I may have burst the balloon. However, in Interactive Physics 2.5, if you don't watch your scaling, it keeps running when you can't see it. And then it tells you the velocities are too high and it kicks out. So I didn't get to see it. But it certainly is something that can easily happen and work through. Here's my recommendations. We really ought to fly a lot of accelerometers. Like I say, the beauty of that Freescale one, not to pick a company, I have no stock in them, but it's 3 analog voltages. Okay? So if you're flying anything that can send down a few cents, any of the stuff you do simple, you can put one of these accelerometers on, a little small package, come down to 3 analog voltages, and have them come down. I mean, Pressure is interesting, particular pressure inside the balloon, but we all basically know what happens to the pressure as we go up. We know what happens to the temperature as we go up. We sort of know what happens to the relative humidity when it goes up. The tilts might tell us some more examples of these encounters, because since the talk, I've discovered that I had some nice video from West Virginia Institute of Technology. They had some nice chaos last December at about 17 kilometers. Okay, so about 55, 60,000 feet. They had a real nice stretch of chaos there that they went through and all. The other thing to go back and do is, those of us that do, like I use the DXG 506B, so I get sometimes the full 2 hours of video. Watch that boring ascent sometime, and all of a sudden go, oh, it was there. You know, you watch it at 4x speed, sometimes that helps you see what happens with that. And the bottom line is, and this is just my final thought before we do the pre-flight briefing this afternoon, expect the unexpected. Thanks.